This video is going to talk about calculating what it feels like to go around a loop. My answer is going to be in meters per second squared for doing this calculation. So to begin with, this is my loop. It's going to be a circular loop to start with. So here's my object, and it's entering the loop at the bottom. It's just begun to go up, just right at the beginning of the curve. So let me fade this out. Let's talk about the forces. To figure out the acceleration that I feel at this part of the loop, I need to look at the forces. I've got the weight going down, that's my weight, as I go around. And I've got the force the track's exerting upwards, which we call the normal force. Together these two combine to give me the net force. So I'm going to have an unbalanced situation here. Because I'm going in a circle, the net force is actually the centripetal force. So here are all my forces, are all set to go. Now I know that the centripetal force is equal to m times AC, the centripetal acceleration. And I'm going to replace AC with v squared over r. Just kind of follow along with what I'm doing here. I'm going to do the same thing for my other forces. Write them in terms of another equation. So my normal force, I'm just going to write that as mass times the acceleration I feel. So as I go around this loop, I'm going to feel a force basically on my bottom. And that force is the normal force exerted by the seat, which comes from the track. So that's what I'm going to be feeling. That's what's going to be turning me around in this direction. And as I do that, of course, I'm overcoming the weight. That's mg. So that ma felt, that's what I'm after. That's the a that I'm looking for in all my calculations. So here are my equations, and what's nice about all these equations is I can see they all have an m in it, and that's going to be handy in just a moment. So now let me sum up the forces and set everything equal to something. To start with, my net force, that's going to be m v squared over r, and that's going to equal ma felt, that's what I'm after, the acceleration I feel on my bottom, minus mg, and minus mg because the mg goes the opposite direction of my other arrows. The masses divide out of everything. So that's great. That makes it real simple. Now I've got A felt kind of by itself in the equation. Next step is to rearrange my equation. So now the acceleration that I feel as a rider, as a passenger, is equal to v squared over r plus g. And that g is 9.8 meters per second squared. So that's the acceleration, and how I find the acceleration at the bottom of a loop as I go around the loop. The acceleration is equal to v squared over r plus 9.8. What about the top of the loop? Well, at the top of the loop, it's a little bit different. The acceleration I feel is equal to v squared over r minus the acceleration due to gravity. So the acceleration I feel is equal to v squared over r minus 9.8 meters per second squared. Notice how these two pieces have opposite signs. And they're opposite signs because at the top the normal force goes down and the weight goes in the same direction. So basically gravity is helping the force the track has to exert to give me my centripetal acceleration. And since it's helping, it'll be a negative sign. Okay, so let's look how this applies to the unit on energy. So here's my loop, shrink it down, and then put it around a hill. So we've talked about problems that where an object starts at the top of the hill and goes down the bottom of the hill. And if I look at this, I can see that if I look at the location at the bottom, I know that the acceleration that I, the passenger, would feel is equal to v squared over r plus the acceleration due to gravity. But the question is, how do I find this v squared? That's when I go back and I use my energy methods. If I know the height and the velocity somewhere else beside the loop, I can relate what's going on to the loop to that other location. In this case, I can look at the sum of all the energy and set that equal to all the energy at the bottom. So I'm using my law of conservation of energy to set these two equal, find the velocity, and once I find the velocity, then I can use a is equal to v squared plus g. So what do I do in a problem if I'm looking, instead of the bottom of the loop, I'm looking for the top of the loop? I can still compare the 2 points, but if I'm going to compare the 2 points, I'm going to get a different velocity because I've climbed up a little bit. And if it's a circular loop, and only for a circular loop, the height I'm going to climb, it's a clever little logic trick, it's equal to twice the radius. In other words, it's the diameter. And that makes sense. If I'm going down to the very bottom, then I go up, and I go up to the top of the circular loop, the diameter is equal to twice the radius, and that's going to be the height I am. So that's the number I'm going to use for calculating the speed at this point. And then once I have the speed, I'll put it in the other equation. AC is equal to v squared over r minus 9.8 meters per second squared. Last type of problem, what if it's an irregular loop? So this could be a clothoid loop or even a spiral of Archimedes, some kind of irregular shape like this. In this case, you have to be given more information. You can't just double the radius. So I need to know where that height is, and I need to know the radius. So the height would have to be given, and then I would use my energy equations to figure out what the speed is, and then use the acceleration that's felt is equal to v squared over r minus g.